Okay, here we go. Okay, so that's what we're going to do today. It would be good to write that, yep. We are going to live and die by that piece right there, okay, yep. Yep, A little squiggly B. So I am a greaser. All right. So this is a new symbol. There's two types of, well, there's many types of calculus. What we're going to focus on right now is we did differential calculus first semester. And now it's an N. And now we're doing what's called integral calculus. And this is what's called an integral symbol. And what we're going to do is this integral symbol, it's going to represent the area underneath the curve bounded from A to B. Okay? So, nope, I would be just an integer that we're going to plug in. Yep. So, this is an I, so it reads, so this actually reads the integral from A to B of the function f of x dx is equal to, and you remember dx, do you remember we talked about that earlier? That's that minuscule change, right? And so that's what we were looking at before. The limit as n goes to infinity, so that's the number of rectangles. The sum, no, it's n, sorry, from I equals 1 to n, so we're going to add up an infinite number of these. F of x sub I delta x, so delta, change in x. And so what we're going to do is, I just have this drawing here. The drawing doesn't match our function, but we have a basic concept here where we want to consider the area beneath the curve of f of x equals x sub 2 from 0 to 2. And you know what that looks like, right? We're just talking about parabola. So that's the area we want to find. Just that. And we're going to start by doing it the way we know how to do it, which is we're going to do just 4 rectangles. So this will get us used to what's happening. Evaluate the right-hand sum using 4 rectangles. If you remember, the way we evaluate the sum is we take the width times what? Sum of the... Yep, sum of the heights, sum of the sequence. We write a sequence, we add it up, but it ends up being the heights of the rectangles. So we can find all the heights of the rectangles, we multiply by the width, because the width of each rectangle is the same, right? So, what is the width of each of these rectangles going to be? 1/2. And you found that by taking 2 minus 0, you divide it by 4. Now, where's the first spot that you evaluate the height? 1/2. Now I'm going to write it like this, just so you understand. We start at 0, and then you went over the width, correct? You went over 1 width. And you're going to square that. Then you're going to start at 0, and you're going to go over how many widths for the next one. You're going to go over 2 widths. Because that's how you get the height. You plug it in the function. And then we start at 0, and we go over how many widths? 3 widths. When we start at 0, we go over 4 widths. I'll show you. Look at this right here. If we start at this spot, okay, whatever that value is, let's say that value is 4, we would, in order to evaluate this height, we would go over one width from there, right? So like we would go over, say, half a unit. So even though we start at 4, the first spot that we evaluate the height would be 4.5. And then we would go over a half a unit more, right? So we went over 2 of the halves, 2 rectangles, so 2 widths. So when we do the third rectangle, we go over 3 of the widths. Then we do the fourth rectangle, we go over 4 of the widths. So that's why I'm multiplying by the width, because that's the increment that I move each time. Okay? So let's just figure this out. That ends up being 1/2 times, what's 1/2 squared? 1/4. 2 times a half, only because we were doing 4 rectangles. So 2 times a half is 1 squared is, I'll write that as 4, so 4/4. 3 times a half is 3.5. 3 times a half is 3 halves. Squared is 9/4. 4 times a half squared, or 16/4. 1 plus 4 is 5, plus 9 is 14, plus 16 is 30. 1/2 times 30 over 4. You get 30 over 8. Or 15 over 4. Or 3.75. You okay with that? Okay. We understand the process for doing a right-hand sum. Now, let's write it so instead of doing n rectangles, instead of doing 4 rectangles, let's do n number of rectangles. What is the width for n rectangles? If the width for 4 was 1/2, what is the width for n? Yeah, exactly. Here's how we find the width. We take b minus a, and we divide it by the number of rectangles. So that's exactly what we're going to do here. B was 2 minus 0 divided by n number of rectangles, or 2 over n. That's my width. For what x values do we evaluate the sum? So you decided to plug in 1/2 and 1 and 1.5 and 2. Okay? What we did is we started at our a, and then we added to that a certain number of widths. So we started, say here, we would start at 4, and we would add 1 width. Then we would start at 4, we'd add 2 widths. Start at 4, add 3 widths. So look at this. See the formula? I equals 1. Then the next one would be I equals 2, I equals 3, I equals 4. So that's the number of widths. So let's plug this in. What is our a value in this problem? 0 plus I times what's the width? 2 over n. So if I multiply that together, I get 2i over n. So this is the width. That's the spot that we're evaluating the sum, or the heights. Figuring out this part for the width and this part for the heights is the most important part. Now the rest is algebra with a little calculus of limits involved. Are you ready? You really got to brace yourself, so you should take a deep breath right now, because the impact is just going to blow you away. Okay, there you go. Okay, you're ready. All right, okay. You can let it out right now. That's all right. Express the area as a definite integral and a limit of a Riemann sum. Let's take this problem. We'll put it into the formula. We're evaluating the integral from 0 to 2. What's our function? X squared dx. So this is notation for saying we're finding the area bounded between 0 and 2 under the curve x squared between that function and the x-axis. That's what that's saying. And we said that we know a formula for that. It's equal to the limit as n goes to infinity. So the number of rectangles is going to go to infinity. Times the sum of all the heights. I start with the first rectangle. I go to the nth rectangle. F of, what is the x value at which I evaluate the height? 2i over n. Times delta x. What is the width? We pause. Everybody see where I got those parts? That's the limit as n goes to infinity of the sum from I equals 1 to n. Now here's what I got to do. I got to plug the 2i over n into my function. What's the function? X squared. So I got to square that guy. What do you get if you square 2i over n? 4i squared over n. Over n squared. Times 2 over n. Can I multiply those together? What do you get? 8i squared over n. How many variables do we have? We got the n and we got the... I'm sorry. Thank you. Okay. So, here's what you do. Okay? We've got two variables, and we need to get rid of one. Okay? And we want to focus on this n piece. We're going to make the I go away here in just a second. And the way that we do that is everything that doesn't have an I is going to get factored out. So I'm going to rewrite this as follows. The limit as n goes to infinity. Remember, do we know how to evaluate infinite limits? We've done it. So we just need something that has an n in it. So I got the limit as n goes to infinity of 8 over n to the third times the sum from I equals 1 to n of I squared. So the only thing I did differently here is I pulled out the 8 over n to the third, so I just have an I squared there. Now you're really wondering, aren't you? We're going to get rid of this. You'll get it. How about this? The first time I did this, it took 3 days before they got it. You guys are going to get it by the time you leave today. I know it. Let me show you. You know what this? Yeah. Oh yeah. You trust me. You guys will be so good at this. You'll be asking me for more difficult problems to do. Trust me. Let me show you here. Okay. We've got summation notation. Okay. You don't write this down. This is an important step. So first time I taught this, I realized that my students had no idea how to do mathematical induction. They had no idea. You guys know how to do math induction, don't you? We don't have to do it. We've already done it. But here's what we did. Do you remember this? if we sum up, this is saying we want to take the sum of the first n number of squares. If you plug in 1 and you square it, you get plus 4 plus very good. And then you're right, you would do the n plus 1. And you're wondering, what does that add up to? Do you remember we proved that it adds up to something? We proved, well, but right, if we add up an infinite number, it would go to infinity, but we're going to stop at a certain number. And we're going to stop at n. And we said that that was equal to does that look familiar? It doesn't look familiar? Alright, so here's what you need to do. Okay? Scratch sheet of paper somewhere or at the bottom of your notes. You're going to write these 4 down because these are really important. So, these are 4 really, really, really important formulas that we're going to need to use. We proved all of them, okay? I'll let you write them down and we'll talk about them. You're going to need to use these over the course of the next 3 weeks, a lot. And you guys got to trust me that right now it seems like a lot of information. After we do a second example, third example, fourth example, we won't get through that today. But as we do more examples, it will become more concise and you will start to see how it all pulls together. You'll start to see the steps. And you'll pause and you'll say, wow, this really is cool. Trust me. So, I'll talk about them. Shh. This says if we add a constant up n times, so if we take 5 plus 5 plus 5 plus 5, it'll be whatever, it'll be 5 times however many times we add it up, right? If you take 1 plus 2 plus 3 plus 4 plus 5 plus 6, it'll be whatever number you stop at times the next number divided by 2. And if you take the squares, 1 plus 4 plus 9 plus 16, it'll be that. And if you take the cubes, it will be that. Okay? We could write one for the 4th, for the 5th. Okay? But we're not going to go that far. We're going to use these. Yes. Just because of the algebra. So like right here we got the 8i squared over n to the 3rd. So that's where the squared is. So this is what we know. Instead of writing the sum of I squared, here's what we can write. Limit as n goes to infinity of 8 over n to the 3rd. This is where we substitute our known sum. We know that the sum of the first squares is equal to n times 2n plus 1 times n plus 1 divided by 6. So all we have to do now in order to find the area underneath that curve is to figure out this limit. Do you know how to find an infinite limit? We do. Look at right away. What do you notice about the ends? I can cancel one of them, can't I? So I end up with just a 6n squared on the bottom. Limit as n goes to infinity. On the bottom, I've got a 6n squared. On the top, let's multiply this out. What's 2n times n? Times 8. 16n squared. Plus 2n times 1 is 2n. 1 times n is n. Add those together, I get 3n times 8. 24n. 1 times 1. 1 times 8. What do you factor out? N squared. You get 16 plus 24 over n plus 8 over n squared over n squared times 6. What happens to the n squareds? They cancel. What does 24 over n go to? What does 8 over n squared go to? 0. You get 16 over 3, or 16 over 6, which is, and that's exactly what it is. You just found the exact area bounded underneath x squared and the x-axis from 0 to 2. You added up how many rectangles? An infinite number! Question. Never! You have to stand up, and you have to stand on your seats. On your seats, you have to applaud. We just added up an infinite number of rectangles. Slow clap. Zero authorities. Okay, have a seat. There you go. Okay. So, do you remember that when I told you how to find the derivative, that right now you know what's the derivative of 6x squared? 12x. But do you remember what we used to do in order to get there? F of x plus h minus f of x all over h, limit as h goes 0, right? The deal is that you found a shortcut. But anybody can use a shortcut, right? In order to understand calculus, you had to learn to use the limit. It's the same way here. Don't stab me, but there's a shortcut. Like, I can look at that problem and tell you it's 8/3. And I will show you the shortcut. But first, you have to show that you know. Here's the deal. If you just know the shortcut, all you know is algebra. This is the calculus that Archimedes was doing way back when, that he knew the answer to. Archimedes used to complain that he knew so many great things about mathematics, there just weren't enough smart people on earth to understand him. And it just, no, it only took 1,800 years before somebody else was born who could really work through his stuff. And so we're doing what Archimedes did. It's unbelievable. Let's do it again. We're going to do x to the third from 0 to 3. What I have to do, we're not going to do the first 4 rectangles. We're just going to start with the width. If you remember, to find the width, you did b minus a over n. Over n, which is 3 over piece of cake, upside down. Now, for what x values do we evaluate the sum? Well, you start at a and you add I widths to it. What's a? 0 plus I times the width would be 3i over n. Easy peasy. Whoa, okay. Let's show you, okay? The a value is 0. Do you see that? I is the number of rectangles. We got to get rid of it later. So I is which rectangle you're using. The width is 3 over n. So I times 3 over n is 3i over n. Got it? Let's express it. The integral from 0 to 3 of x to the third dx is equal to the limit as n goes to infinity, infinite number of rectangles. We got to find the sum of the heights of the rectangles. We start with the first rectangle. We go to n rectangles. F of, where do we evaluate the heights? 3i over n. Times the width. The sum of the heights times the width. What's the width? 3 over n. That's your delta. Very good, Larry. Limit as n goes to infinity of the sum from I equals 1 to n. We have to plug 3i over n in our function. When you take 3i over n, you plug it into the function, what do you get? 27i cubed over n cubed times now. We got to get rid of that whole sum piece, right? But we can't do it yet because we've got i's and we've got n's together. So we want to get rid of everything that doesn't have an I. So the numbers and the n's, we got to pull them out. Yep, we cubed 3i over n. We got 27i to the third over n to the third. Because it says f of. You got to plug it into your function. So the limit as n goes to infinity of, okay? Good, so 27 times 3 was, we take out that 81, and n to the third times n was, so we take out the n to the fourth, we have the sum from I equals 1 to n of, what's left? I cubed. Do you know what that is? Very good. That is n squared times n plus 1 squared over 4. Yeah! Limit as n goes to infinity of by 81 over n to the fourth times, we know what that is. We wrote a formula for it. We proved it using math induction. N squared times n plus 1 quantity squared over 4. What do you notice about the n squared? Cancel with the bottom will go to squared. Do I know how to do an infinite limit? Before we take out the n squared, let's actually multiply this out. N plus 1 squared. I'll have n squared times 81 is, then n plus 1, the middle will give me 2n times 81, 162n. 1 times 1 is 1 times 81 is 81. And that's all over what? 4n squared. Limit as n goes to infinity. What do you take out of top? N squared times 81 plus 162 over n. 81 over n squared. The bottom we got n squared times 4. What happens to the n squareds? What happens to 162 over n and 81 over n squared? So you end up with exactly. See? You. No. The other two examples. Now, here's the deal, guys. Okay? We're going to make it just a little bit different. I changed the bounds. So same thing, x to the third, x squared, x to the third. But here's one change I'm going to make as well. Okay? We're going to do 2x, I'm sorry, we're going to do 3x squared. So all that happens is, it's just the constant 3 just comes along for the ride. That's it. When you plug it in the function, it'll be 3 times whatever you get squared. Yep. And then instead of x to the third, we're going to do 1/4 x to the third. See if you can just work through those two. Because if you can work through those two, trust me, tomorrow is going to be a lot easier. Because tomorrow what we want to do is instead of starting at 0, we want to start at, say, and instead of doing just 3x squared, we want to do, say, 3x squared plus 2x minus 1. So we want to stretch it out a little bit. But the process, you get it now. You can roll with it. And it's really, the second time we did it really wasn't that bad, was it? So it's up to you now to solidify your learning and really, get to this tonight. Don't let it sit, okay? If you need to watch video again, you can watch video. I'll check the video from tomorrow.